Hello and welcome to
The Embedded Frontier Podcast.
I'm Jacob Beningo, and today we are going to be talking about Baremetal, POSIX, and the future of real-time operating systems. Now, I don't know about you, but there's lots of different ways that you can go about developing an embedded system, right? Different paradigms, different design patterns. And one of the most traditional ones that you can possibly use is bare metal. And if you were to stop and think about bare metal development, you might be saying, who actually develops in a bare metal way anymore, right? Haven't real-time operating systems conquered the industry? Isn't 100% of the systems built today going straight to a real-time operating system? And the fact of the matter is, that's not the case. In fact, if you look back at the embedded market surveys over the last 5 years, you'll find that there has literally been almost no change in the percentage of real-time operating system use versus just pure bare metal development techniques. And so for some of you who are working in bare metal, that might make you relax a little bit, right? Some job security there. That doesn't mean you have to become an RTOS expert in order to keep your job and develop embedded systems. But I think it does show an interesting point about what's actually happening in our industry, right? And so while RTOSs have become very dominant in the embedded systems industry, it has really so it's kind of steadied, right? It's not changing as an overall percentage of the systems that we are designing. Now, the thing that's probably interesting about that, there was a rapid rise, right? Prior to those 5 years of people who are adopting real-time operating systems. And most likely that was really due probably to the adoption of internet connected devices, right? The IoT was strong. It's still strong, and it's driving a lot of new designs and development. But at the same time, that's a lot of 32-bit processor usages, right? Lots of people are using Cortex M's of some sort, right? M33s, maybe some of the later ones, Cortex M4s and things like that, right? And so as you start to think about this, well, why have not the RTOS actually kind of taken over a little bit more than just those, 66% essentially. So what they're finding is about 2/3 of embedded systems are using an RTOS, the other third are not, okay? And so when we try to start to figure out where is the future of RTOS actually going here, are all the systems going to go to an RTOS, or will there always be some bare metal? The fact of the matter is, you can very easily kind of start to get an idea of why that might be if you go over to your favorite hardware vendor. Okay, and so what do I mean there? Well, go over to DigiKey or Mauser or Future or whoever your favorite vendor is. Go over to their website and look at the microcontrollers that they have. Okay, so right now I've got the DigiKey page open here. I've done a search for microcontrollers, and what I find is that there's 81,528 different microcontrollers that you can choose from. Talk about a lot of different microcontrollers. And the fact of the matter is, DigiKey probably doesn't even sell all of the possible ones that are out there, right? But they probably sell a good portion of them. And so, man, almost 82,000 microcontrollers out there in the market. But through a very quick search here, we could just take a look at the core sizes and start filtering some of these. So if I look at, are there people still using 8-bit microcontrollers out there? Well, if you take a look, almost a quarter of the microcontrollers that DigiKey provides or sells, there's 24,239 of them that are actually from 8-bit microcontrollers. In fact, I said a quarter. That's totally wrong. Horrible mental math. Almost a third of all the microcontrollers that are provided are going to be 8-bit microcontrollers. Okay, and so that's huge. If you're using an 8-bit microcontroller, chances are you're not going to be using a real-time operating system. Now, yes, of course, 8-bit microcontrollers, 8-bit technology has actually progressed a long ways from where it was, 5-10 years ago. If you were to look at, for example, I started out on an 8-bit microcontroller back in the late 90s. I used a PIC16F84 microcontroller. That microcontroller, sported a wonderful 2K of flash space and 256 bytes of RAM. Okay, there was no chance of putting a real-time operating system on that thing. It did, bare bones. I had to program it in assembly and all of that kind of stuff, right? Very fun. But of course, compared to today's systems, there's just not enough, flash space there. But if you do look at today's modern microcontrollers, you're going to find that these things actually have quite a bit of memory associated with them. And so while they might be 8-bit machines, you can find program memory sizes that range all the way up to, I'm doing a quick filter here, all the way up to 928 kilobytes of program memory. Okay. And so, yes, they're 8-bit machines, but they have grown substantially in how much memory they can support, just like a typical 16-bit or a 32-bit microcontroller. Okay. And so while there is all of that support, you very easily could potentially put an RTOS on those. Okay. But when you look at most of the applications that are really in that little 8-bit arena, these are little applications that typically never were benefiting from any type of intelligence, and people are just adding a little bit of intelligence to these systems. They can be found in all kinds of interesting systems, and again, they actually are still dominant. They're not going away by any means. Okay, 8-bit machines are still going to be around for quite a while. Okay, so that's probably enough to talk about 8-bit machines, right? Probably a lot of you are working with 32-bit microcontrollers, right? And so if we actually go and take a look at your standard 32-bit microcontrollers, what you're going to find that is super interesting is that on DigiKey's website, and this doesn't quite seem right. They're saying there's only 5,500 32-bit machines, which I think is not going to be accurate here. I probably have a horrible search that's in there. We'll try that again. Okay, so here we go. 31,000 microcontrollers that are going to actually have that are provided by DigiKey as an example. Okay, and so not quite half the industry, but definitely probably a good 42% of the industry is 32-bit microcontrollers now. And again, this is a big drive from IoT connectivity. You're going to be looking at devices that need something to help them manage complexity, right? If you're talking about building IoT devices, which many of us are, we're building IoT devices, we're building smart devices, starting to use machine learning and AI in our designs. You're going to have to be using something that can actually provide some power, right? If you actually look at a lot of the modern microcontrollers, you're actually going to find that many of them are starting to be multi-core. Okay, multi-core is coming in the microcontroller space. And as part of that, that adds an interesting spin on how we are going to be designing systems. Okay, especially using a real-time operating system. You have to make decisions like, are you using the same RTOS on all the cores? Or is there going to be a combination of asymmetric and symmetric processing? Or are you going to have some of those cores that maybe that are running bare metal? Okay, we could have systems that are following multiple design paradigms all working together. And some of that is going to, of course, very much depend on what it is that you are doing and what some of the core goals of your design in your system are, right? As far as scalability, performance, real-time processing capabilities, and all of that cool stuff. Looking on DigiKey's website, I'm seeing some really interesting things like where you can get a 32-bit processor, with 10 cores, and that's supposedly a microcontroller. Okay, I've not personally played with those. That seems like quite a bit. That's pretty crazy. But as you can imagine, again, that doesn't surprise me to some degree, because what we're going to start seeing in the microcontroller space is partitioning up of our application space. Okay, pretty soon we're going to see, okay, well, I'm going to have a very complex system. I'm going to have one core for AI. I might have a core for processing my digital signal processing, and I'm going to have another core for doing my real-time stuff, and I might have another one for managing my display, and another one for so on and so forth, right? And to some degree, if you look at some of the newest microcontrollers, you will actually see that, right? They're providing AI hardware accelerators. They're providing digital signal processing encoders, hardware accelerators for cryptography, and all of those kinds of things, right? We'll have secure cores, unsecure cores, and kind of the list just goes on and on, okay? And so, wow, this is a lot of stuff that we're going to have to be worrying about. Where do real-time operating systems come into play here, right? And while we certainly will be always leveraging some bare metal techniques, bare metal is not going to go away. The thing that's really interesting is RTOS technology, okay? And what an RTOS is basically doing is it's just providing you with a kernel to help you schedule your tasks, your activities for your system in a real-time manner, right? Providing some determinism and, it's different algorithms like time slicing, cooperative scheduling, but most importantly, preemptive scheduling, right? The ability to prioritize threads, so that if one thread is running and something more important in the system happens, that thread can cause a context switch that will then allow that higher priority thread to actually execute, okay? And so developing with a real-time operating system really helps to simplify how we manage time and how we can break our system up to make it more scalable, reusable, and more maintainable, okay? And so that's why you'll find most 32-bit applications today will go straight to a real-time operating system. Now, if you are going to a real-time operating system, one of the things that you might often ask yourself is, what are you going to do with those? How are you going to choose your real-time operating system? There's actually a lot of different RTOSs out there. If you were to actually go and check out Wiki or do a search online for real-time operating system, you're going to find that there are more than 100 different real-time operating systems out there that you can use to develop your embedded system. Now, I'm going to be honest, that's really hard to make a choice, right? If you're given 3 choices for dinner, it can sometimes be hard just to choose what you want to have, right? How are we supposed to choose from 100 different flavors of real-time operating systems, right? Because the fact of the matter is, no 2 RTOSs are actually identical, okay? There's not a standard for RTOSs out there where, every person who's developing an RTOS actually follows some specific standard, right? Everybody has a little spin or a flavor that they are looking at that their RTOS does to help the people that are using their real-time operating system. And let me give you an example of that. If you are interested in trying to develop an embedded system following the paradigms of embedded Linux, you might in fact choose NutX as your RTOS. The reason for that is that it is trying to be like a mini Linux, okay? It gives you kconfig device trees. It gives you a lot of configurability. The way you design and build your applications in many cases are going to be very much like you're running on a Linux-based system, okay? On the flip side of things, you might have other RTOSs that are providing you with more of a bare metal approach, right? For people who are maybe coming from a bare metal development environment and they're just trying to help clean up their design, have it nicely separated out, right, and architected, and have some help with managing preemption and the scheduling of their tasks in their system, right? And so what that's going to do is that's going to make other RTOSs, things like FreeRTOS, ThreadX, and maybe even RT-Thread or maybe even a Zephyr to be an operating system that maybe someone would be interested in, okay? And just from that conversation there, you've heard I've already mentioned 5 different real-time operating systems that are out there. FreeRTOS, ThreadX, which has actually become Eclipse ThreadX now, which is actually really interesting. We'll talk about that in a minute. And then, of course, there's, as I mentioned, Zephyr, which has become having a snowball effect right now into the industry. The amount of adoption and effort that's going into Zephyr right now can almost make a developer's head spin, okay? There's a lot of great things going on there. We'll talk a little bit about some of those things here in a little bit. But beyond the RTOSs I've just mentioned, these are mostly open source RTOSs I've just mentioned, right? FreeRTOS, ThreadX, Zephyr, NutX, RT-Thread. But we're not limited to our choice of just open source. There's also commercial real-time operating systems, right? Ones like MBOS from Sager. There's VxWorks, Integrity from Green Hills. And so the level of robustness, the security requirements that you have, even safety certifications, those types of things are going to help drive you towards a type of real-time operating system that's going to work best for you in your own designs. Now, one of the things here that if you are trying to figure out how do you go about deciding which real-time operating system you're going to use, there's a couple of ways that you can go about doing that, right? The one that I've seen a lot of teams use, which I do not advocate in any way, is that they just simply pick the real-time operating system that is supported by their vendor, okay? And what I mean by that is they'll go over to, like, for example, the ST Microelectronics tools, and, it might support ThreadX and FreeRTOS. And they'll just kind of look at that and say, okay, well, between those 2 tools, I like FreeRTOS better, or I like Zephyr better, FreeRTOS better. And what they will do then is they'll just use what's supported and provided for them out of the box from their silicon vendor. And it's the same thing. If you look at, any vendor, NXP, Silicon Labs, Nordic, pick your favorite vendor. They all provide you with kind of a baseline RTOS in order to try to help you get up to speed faster using their parts. And to be completely honest, that's fantastic, right? We should thank them for that, right? They've made sure the ports are good. It works on their hardware. It's fantastic, right? But what it's also done is it's also sometimes made us a little bit, compliant in that we don't really think about the needs of the real-time operating system. We view it as a black box. And from there, we just say, well, any old RTOS will just do, right? Because they all do the exact same thing. And the fact of the matter is they don't. You'll actually find that every RTOS does provide specific, interesting differences that can help make or break your application. Now, as we think about those types of things, okay, so it may turn out that the vendor provided RTOS works perfectly fine for what you're doing, okay? But at the same time, you always should go through and actually perform an engineering analysis. Does this actually work the best for me? Now, one of my favorite techniques to actually go about doing this is to actually use a Kepner-Trigot matrix. Okay, these are often called KT matrices, and what these do is it actually helps you make an unbiased decision to select your real-time operating system. And this KT matrix technique, it can be used to help you make an unbiased decision about anything. Okay, if you're trying to decide between 3 different microcontroller vendors, or you're trying to decide between, I don't know, 3 potential engineers to hire, or what sensors you should be using, and that sort of thing, it can be used to make any unbiased decision. Okay, if you really want an unbiased decision about what you're going to have for dinner tonight, you can make a KT matrix. Okay, the idea behind these is that you take a look at what you basically go through and you categorize what is important in your decision. Okay. And so, like, for example, if I'm going to select a real-time operating system, I might identify things like, well, does it have, what's a license that's associated with it? Is it open source? Can I modify it? Can I, see the source code? I might have things like, well, how, maybe there are, what's the size of the RTOS? What are the capabilities? Okay. Does it have the ability to broadcast messages and signals? Okay. A lot of real-time operating systems actually don't allow you to do that. Okay. And so, identify key pieces that are required. Even engineer familiarity, support for your microcontroller, all of those types of things are decision points that you would want to consider. Does it offer, security capabilities? Can it interact with the memory protection unit? And what you do is you identify the things that are important for you to have in your design, and you list them out. Okay. Once you have that list, you can go through and you can identify and weight how important each of those criteria are going to be for your decision. And so, for example, what's a major decision driver for a lot of teams? Cost, right? And so cost undoubtedly is going to be weighted with, let's say on a scale from 1 to 5, it's going to be given a 5, right? Cost is very important. Many teams don't want to go out and spend $30,000 or $50,000 on a real-time operating system, right? They want to, if they can, get it for free. And if not, they want to maybe spend $5,000 or $10,000, right? Something much smaller and manageable versus, $30,000 a year, right? We can start hiring people almost for the amount that the license actually costs. Versus, or if it has a fee per device or whatever the licensing model has to be, right? And so you go through each of these decisions, and on a scale of 1 to 5, you basically rate how important that is to the decision. Then after that, what you do is you get your decision makers together. There's probably, 3 to 12 of you. Okay. And then each of you go through and you rank on a scale of 1 to 5, how well each RTOS that you're trying to decide between matches the criteria that you've set aside there. Okay. Now, as you can imagine, what you're going to end up with there is the ability to create a weighted average, right? You have each person kind of weighing in on a scale of 1 to 5 on how important that is. And you can, average those out, or you can, multiply each of those by the weight and then sum them all up. And then that will give you some value, numeric value for the particular criteria. Once you have that, you can sum up all of your criteria and all of the ratings, and that will give you one numeric number for each of the RTOSs that you're evaluating. And as you can imagine, the RTOS with the highest value is actually best suited for your particular needs. Okay. And so that becomes a very easy way to get an unbiased decision. You don't have, one engineer trying to strong arm you saying, I want to use this RTOS, and, kind of throwing a fit or anything like that. Not that we do that. We're all very professional, right? But you get the idea, right? We get a nice unbiased decision that we can follow. And again, this is the KT matrix. Now, of course, just because the KT matrix says this is the numeric value, again, you may have to weigh in extra on costs or convince a manager or, your team that this is actually the right way to go. It could have other repercussions, right? If you're using an RTOS that you're not, your team's not familiar with, well, now you have to train them. You have to potentially get support, and that could have other impacts on your time to market and those types of things. Okay. And so you do have to take all of that into account. But again, don't blindly select your real-time operating system. I have seen teams get in trouble by selecting the wrong RTOS. The things where, maybe the cooperative scheduler wasn't actually deterministic, or where they thought it had some feature and it didn't. Or I've even, I'll give you an example. My very first use of a real-time operating system turned out to be with an RTOS that actually was commercial and wasn't a real RTOS. Okay. It just provides some cooperative scheduling, and it provided like semaphores and mutexes and some queues, but it really didn't provide preemptive scheduling. It didn't provide time slicing. It was actually very poorly written. We spent more time trying to get the RTOS to work the way that an RTOS was supposed to work than we did in developing our actual design. Okay. And after that complete headache, fighting all kinds of interesting bugs for several years, I was like, yeah, no, RTOSs are horrible. I'm never going to use one. Right. And then I think I came across free RTOS and played around with that. And I was like, oh, wow, okay, this is the way maybe an RTOS is actually supposed to work. Right. I not to, promote free RTOS or anything. We can nitpick any RTOS out there, right. Based on certain things. So, but again, very popular, has done wonderful things in the industry, right? We can't really say anything bad about any of these open source RTOSs because they've provided all of us with some great tools that we can use to get our jobs done, right? And okay, so I think that gives you some ideas of baselines related to real-time operating systems, things that we should consider when we are selecting them, like I said, licensing costs and those types of things. Now, when we start to stop and think about the future of real-time operating systems, I think that there's a couple different routes that RTOSs can take here in the future. Okay. The first one, of course, is that open source really is a major driver in our industry. Okay. If you're building an embedded system, pretty much we're using as much open source software as we possibly can. Okay. Not sure, again, you can end up with very nice, high quality libraries, lots of great things, right? And if we don't have to pay exorbitant fees for it, then fantastic, right? More eyes that are on things, the chances are the more we're going to be able to get rid of bugs and improve performance and those types of things. Okay. Open source is kind of a gift to us and really makes it so that we can build more systems. Now, of course, if you are working in a safety critical or mission critical environment, open source software may not be the right approach. Although even that to some degree is changing today. Okay. And so if you were to look at, for example, Eclipse ThreadX, okay. And you might say, well, what's Eclipse ThreadX? Well, that was originally Azure RTOS. And before that, it was before Microsoft had bought it actually from Embedded Logic, and it was just the ThreadX, just ThreadX, okay? But it's still the same core real-time operating system. It's just kind of been kind of moved around, but it's just becoming open source through the Eclipse Foundation, okay? It was just announced a couple of months ago. And so this is kind of a potential game changer, right? We have a commercial RTOS that was safety certified, that was certified for security as well, has been very robustly built, and now suddenly it's open source, right? And so that gives us a commercial quality RTOS at open source costs, okay? And if you're going to be doing something that's safety or security related, it's been designed in such a way that you can still take it and get it certified for your uses, right? And so that suddenly makes it so that you're not paying the overhead costs of the RTOS, right? The commercial side of it, but you might still be paying something in order to do the safety and security certifications. Now, kind of related to that, we've got Eclipse ThreadX. We also have Zephyr, okay? Zephyr has, I remember the first time I heard about the Linux Foundation saying, hey, we're creating a new RTOS and it's called Zephyr. And my response was literally, oh, great, here we go. Yet another real-time operating system, okay? Now, perhaps that's a very pessimistic view of that. But, over the last couple of years, that pessimistic decision, to some degree, I regret it because Zephyr has started to provide some very real interesting, true open source types of capabilities for developers. They've built this with the idea of it being an IoT real-time operating system where security and safety are critical in the design, right? It's completely open source, which means you or I can go in, we can make changes, and we can request that those changes be put into the kernel. And if you look at how Zephyr actually works, it's quite interesting because we can use it in kind of a threadless manner. We can use it in a way that's kind of similar to like a free RTOS or ThreadX. And at the same time, if we really want to push far, we can use it in a way where it is, it in itself, it is actually allowing you to it provides the vice tree and kconfig. So it borrows concepts from Linux that allow us to kind of almost increase the number of embedded developers there are, right? Because if I am familiar with how Linux works or embedded Linux works, it makes it a little bit easier for me to move over if I can use that type of model with a real-time operating system, okay? And that's kind of also what NetX does, right? NetX literally tries to be mini Linux. Zephyr does not. Zephyr's trying to be a real-time operating system, but it does borrow from concepts from Linux. Like I mentioned, device tree, it has kconfig, and then it also has the capability, there's a thing called the Zephyr bus, the Z bus, which allows you to broadcast messages and kind of provides things for your application to be more scalable and reusable. and more adaptable. And in addition to that, they kind of borrowed the concept of the dbus from Linux in that respect. But again, some of these features, they are evolving quite rapidly. If you were to actually go and look on GitHub at the number of contributors to Zephyr and the number of commits they're doing per month, it's amazing. It's huge, right? They're going to reach over like 100,000 commits or something like that very shortly here. And right now it's probably it's the RTOS, the open source RTOS that has the most contributors and commits, and probably, as I was mentioning, it's snowballing. Okay. So, Nordic several years ago kind of started to get involved in it, really started pushing it forward. And, all the announcements that we're starting to hear in the industry is, from ST, from NXP, from, pick your favorite silicon vendor, they're all starting to jump on the bandwagon of supporting Zephyr with their microcontrollers. And so what that means is that, Zephyr is starting to become, be put in a position where this might be, the operating system that over the next 5 years really gains the most support. Okay. And the most users. And the interesting thing about this is it's a open source real-time operating system where the community is driving it. The community has control of it. And, they're still following best practices and really trying to ensure that it has, interesting things like, SBOMs, right? Software bill of materials. These are things that you need if you're building, medical devices or anything that's going into, safety critical, or, where maybe I'm using a library from, some vendor, and we find out that there's a security vulnerability, right? Well, we can be notified about that because we can actually generate the SBOM and, kind of show people, hey, this is the software that's actually in our systems that, we're using to do productive work. Okay. And so again, some really exciting times. You would think, well, real-time operating systems have been around for decades, right? There's nothing interesting going on there anymore. But we would be wrong. Okay. There's so much interesting going on there. So much still to learn, new design patterns, new paradigms that are coming out. All of these things designed to really help us develop embedded systems faster, more reliably, more scalably. Okay. And maybe scalably is not a real word, but I'm going to use it here anyways. Okay. And so as we look at the future of real-time operating systems, I think we're looking at probably the adoption of these open source ones like Eclipse ThreadX and like I said, Zephyr. I think this is really probably a driving force behind real-time operating systems today. Okay. And, the way in which we use these can integrate very easily into like our DevOps pipelines. We can simulate on these on Linux machines and Windows machines. We can easily move them from one system to the next. And so as you start to think about this really brings us to, how are we going to start to design our RTOS-based applications, right? And so, a lot of teams are trying to build platform-based systems. These systems are going to be, I'm designing a product today. I want it to be supported for the next 10 years. And from that software I'm writing, I may want to launch a dozen or 2 dozen products off of that same software. And so how do I go about designing that? How do I architect those types of things, right, with an RTOS? And the future of how RTOS are going to be used and how we're going to design these RTOS applications is going to depend on the RTOS we use and the model that we select when we design our software. And so right now in my mind, there's actually 3 different models that we can follow. The first one is an independent model. Okay. In an independent model, this is where we take the design paradigms from like FreeRTOS or ThreadX. Okay. This is where we look at it as the RTOS is not the center of our design. The RTOS is a component. It's middleware that's provided to help us develop and architect our systems. And so we might have at the lowest levels our hardware. We may then have drivers, and then we would have above that, our RTOS, our middleware, and above that, our application. Okay. And so the RTOS is a way to help us build our application. And maybe we have an OSL, CMSys RTOS v2 or something like that to help us abstract out the RTOS so that the RTOS does not become a major coupling point or a major dependency in our applications. So that's the independent model. There's also a dependent model. And the dependent model is where we say the RTOS is key and critical to our design. And so instead of us trying to really decouple from that real-time operating system, we instead really strongly adopt it. Okay. We leverage it to the tilt. And, for example, Zephyr is actually a reasonable RTOS to look at for this dependency model. Okay. And the reason for that is that it's not just trying to, in its standard architecture, provide you just with the tools to be able to, create threads and coordinate them and that sort of thing. They've built in the hardware abstraction layers and the APIs to allow you to be able to manage the entire board, to use kconfig to select components that will be in and out of your system, to create device tree overlays. Okay. And so these types of things, it's not just trying to be an RTOS to some degree, but provide you with abstractions and an OS level of architecture and development. Okay. And you don't necessarily have to go that route with it, but that's some of the things that it's enabling. And that does open the door for non-embedded folks to be able to develop products and write software for these types of systems, right? Because they can work at a higher level and not have the understanding of what's going on behind the scenes and underneath the hood, right? And so that dependent model is really kind of the second model that we can look at here. Now, the third one is, I don't know that it's necessarily a separate model, but the idea here is that it doesn't care whether you have an independent model or a dependent model. What it does is it leverages POSIX interfaces. And so the idea here is that the future developer who's using a real-time operating system, instead of having their code tightly coupled to, a dependent modeled RTOS or an independent modeled RTOS, instead, their application just uses POSIX interfaces. And what this does is it allows them to develop an application in such a way that they don't care what operating system they're using. Okay. And if you do that, FreeRTOS has POSIX interfaces. So you could be developing an application and say, yep, I'm going to use FreeRTOS on this product because maybe it's consumer grade. And then alternatively, you could say, well, on this one does require some safety and security. So maybe I'm going to use, ThreadX, or ThreadX doesn't have POSIX interfaces. PX5 does. So that could be an option, a commercial real-time operating system. But maybe I say, Zephyr, I'm going to use a Zephyr POSIX interface, right? Or, as part of that, maybe I say I'm going to have multiple products and one of them is going to run on a microcontroller. And so we're going to be using, let's just say NetX in this case. And then in the future, we might use it on Linux. And so if we write it to support POSIX, then we can very easily move it over into a Linux environment. Or if I'm using POSIX interfaces, I can test my application in my DevOps pipelines, right? And so I can end up with code that's a lot more portable and reusable. And if I have portable, reusable code, then that means I have a lot more options to me. And I can make that application that I designed, I can make it last longer. I can maybe get it so that I can support it for 10, 15 years in the future because I'm using a common interface within the industry that's already well known. Okay. And so, so when we stop to think about that, these are some of the models that developers can use today and into the future. I think as we look at real-time operating systems, there's a lot going on. There's still a lot of changes happening. And I think that you're going to find that real-time operating systems, it's always a great idea to know how to use more than one. And how you go about, we've talked about how you can go about selecting them. And I think that you're going to find that it's an exciting area to be in. And I hope that you'll take some time to learn a little bit more about the different models that are out there, how different RTOSs work, and then to learn how to effectively architect an embedded application that does use an RTOS. Okay. Because what you will find is that as microcontroller cores grow, as the capabilities of our edge devices start to grow, not only are we going to be integrating artificial intelligence, we are also going to have to be making mixed systems that rely on real-time operating systems and also on bare metal design techniques. In fact, I wouldn't be surprised if some of you in the future will develop systems that use not one, but maybe multiple real-time operating systems simultaneously across cores and use bare metal techniques as well. Okay. It's an exciting time for embedded systems. And I'd like to thank you for joining me today to talk a little bit about bare metal, about POSIX, and what it provides for us in developing our applications. And then of course, where real-time operating systems are today and where they'll likely go tomorrow. Okay. All right. With that in mind, I wish you the best of the day, and I look forward to speaking with you next time.